Let's start with this idea of span. And we say the span of some vectors, the span of a collection of vectors. If you've got some collection of vectors, like let's say vectors v1, v2, and v3, we usually say we're talking about a set or a collection of things by putting them in curly brackets. So this is a collection of vectors. It's just 3 vectors. A set of 3 vectors. But if we talk about the span of those vectors, the span of a collection of vectors means a new set of infinitely many vectors, specifically all possible linear combinations. And have you seen yet what we mean by linear combinations of vectors? If we're talking about a linear combination of, in this case, v1, v2, and v3. First of all, is there any operation you can do to a vector that doesn't change which direction it's pointing?
Is it multiplying it?
Yeah, you can multiply it specifically by a scalar. So let's say we take each one of these vectors and multiply by a scalar. Let's say we call this C1, C2, and C3. So C1 times V1 is a new vector pointing in the same direction as V1, or maybe the exact opposite direction if C1 happens to be a negative number, but maybe having a different magnitude. For instance, if V1 is 5 units long, then like 3 times V1 would be 15 units long. The scalar just rescales. In fact, this is why they're called scalars. They literally just rescale the vector to a new size, but pointing in the same direction or the exact opposite direction if the scalar is negative. So C1 V1 would be a new vector parallel to the original V1. C2 V2 is parallel to V2. C3 V3 is parallel to V3. We can also combine these to get a new direction by adding them together. So if you take some multiple of the first vector, and by multiple, it doesn't have to be a whole number multiple. You could have like 3.7 times V1 or square root of 2 times V1. So some scalar multiple of the first vector plus some scalar multiple of the second vector plus some scalar multiple of the third vector. That combines them to get a new vector in a different direction that's somewhere, some diagonal between these. And this is called a linear combination of those vectors. Any questions on that so far? And in general, from now on, when we use the word linear, it's usually going to mean having something to do with a linear combination. And part of the reason it's called that is if you're just talking about one vector, linear combinations of one vector are just multiples of that vector. And if you take a look at that on, let's say, an XYZ axis, if you just got a vector, let's say some vector in the YZ plane, if you consider all possible multiples of that vector, you get like another vector that's in the same direction, but longer or shorter or much longer, or maybe in the exact opposite direction. But all those vectors together are going to form what sort of shape?
A triangle?
Not a triangle, because you're only going in
or just a straight line, right?
Yeah, if you just have one vector and multiples of that one vector, including
that makes sense.
multiples to the opposite direction, that's just going to be creating a straight line. And it's kind of a blurry distinction between the vector and the location it's pointing to. But if you consider all the locations pointed to by these vectors, they all form a single straight line, and in particular, a straight line through the origin. A straight line that includes 0, 0, 0, because of course this scalar could just be 0 times the vector. So the span of a single vector, the span of just one vector, is a straight line, if you consider all possible results of a scalar times that one vector. So the span of one vector is a straight line. If we add in another vector, so the span of two vectors, let's say we add in the possibility of going, the second vector is this direction. Let's say that's V2. So the span of V1 is just a straight line, a one-dimensional region. If we consider V2 though, all multiples of V2 would be another straight line because we're going as far as we want in the V2 direction or the exact opposite direction. So the span of V1 alone is this line. The span of V2 alone is this line. But if we consider the two of them together, we can go not only in the direction of V2 and not only in the direction of V1, but we can also combine them. We can go some distance in the V1 direction and some distance in the V2 direction, ending up here on this diagonal.
Okay.
So we get these diagonals. We can go like this far in the V1 direction and this far in the V2 direction and get this diagonal. Or this far in the V2 direction and then in the negative V1 direction and get this diagonal. Or this far in the negative V2 direction, this far in the negative V1 direction and get this diagonal. So we can now, by combining them, we can get to a lot of new locations that aren't on either one of those lines. But if we consider all those possible locations, linear combinations of V1 and V2, what sort of region of space do we form here?
That would just be an XY axis, right? Like R2?
Yeah, well, it's not exactly R2 because it's not necessarily on the X and Y plane, but it's on some other plane. In the sense that
it creates its own plane, right?
Right, it creates a new plane that might or might not be the XY plane. But you've got, let's say, the V1 direction and the V2 direction. So each one of those individually would form a line. But if you can also consider all the points that you can get to from combining those, you get all these in between points and these points. So yeah, you get an entire plane. So the span of two vectors can create an entire plane. And we call that plane, how many dimensions would you describe a plane as?
Two.
Two. And we call it two-dimensional because you need two vectors to build it. So a plane is the span of two vectors. A line is the span of just one vector. So we call it one-dimensional. And if you add in a third vector, a third dimension, let's say a vector in this direction, the first two vectors create a plane. So first two vectors, let's say, create this plane. A third vector adds a third dimension. So now by linear combinations of V1, V2, and V3, you can get to anywhere in a three-dimensional space. So if the universe we're talking about is R3, then three directions is enough to get to anywhere in that entire universe. However, if you're talking about a higher dimension universe, like R4 or R5, three vectors wouldn't span the entire universe. They would just span a three-dimensional subspace of that universe. So 3 dimensions doesn't have to be the entire universe if we're talking about like R4 or R5, a higher dimensional vector space. But generally, dimension is the number of vectors that are required to span the region we're talking about.
All right.
So just to sum up, you could have a collection of finitely many vectors, but the span of those finitely many vectors is a new set of infinitely many vectors consisting of all possible linear combinations. Any other questions on the terminology so far?
I do have one question about symbols. There's one formula they told us to memorize in class that was what translates to the dot product that has, it's a double absolute value of V times W times cosine theta. And I'm not positive, but I think that's magnitude, correct?
The double absolute value is, yes.
All right, and then how do we calculate that? It's been a little while.
Magnitude?
Yeah.
Yeah, let's take a look at magnitude next. Before we move on to magnitude though, any other questions on the idea of span so far? Okay, so getting into the idea of magnitude, and this is closely tied to the concept of dot product. So we want to look at that as well. We keep taking the dot product of two vectors. Like let's say we have, let's say vector u is a, b, and vector v is x, y. Well, let's make these 3 by 1 instead of 2 by 1. Let's say vector u is a, b, c, and vector v is x, y, z. So these are both vectors of R3 in the sense that they are both just a single column of, in this case, 3 real numbers. So A, B, C, X, Y, and Z are all real numbers, scalars. If we want to calculate the dot product, U dot V, that is ABC dot XYZ. Not multiplication, but dot product. How would you actually write that out? How would you expand that dot product? Yeah, multiply the matching components, A times X plus B times Y plus C times Z. So that's typically how you would define a dot product, as long as you're talking about vectors in R to the n. So this applies to any vectors in a space written as R to the n. If you're talking about vectors, because we're going to be looking later on at vectors from different spaces, vectors that aren't just columns of real numbers, but still act like what we can call vectors. So there are different ways to define dot product in different vector spaces. But if you're talking about R to the n, dot product is typically just defined as multiply the matching components and then add them up. Which does mean they have to be matching sizes of vectors in the sense of 3 by 1 and another 3 by 1. You can't take the dot product of, for instance, a 3 by 1 vector and a 4 by 1 vector. They have to have matching dimensions. Any questions on that so far? And an interesting thing happens if you try taking the dot product of a vector and itself. If you take the dot product of ABC and itself, what would you get?
A squared plus B squared equals C squared. So
A squared plus B squared plus C squared. Yeah, we're adding A times A plus B times B plus C times C. However, that does look a lot like what concept from geometry?
The Pythagorean theorem?
Yeah.
No.
It's almost, I mean, it's missing the square root, but this is essentially the Pythagorean theorem for 3 dimensions. If you've got, let's say, an x-axis, a y-axis, and a z-axis. If you've got a vector that is, let's say, A in the x direction plus B in the y direction, and then some distance C in the z direction, so you're going from the origin out to this location. So going out A in the x direction and B in the y direction, and then from there up C in the z direction. In that case, the Pythagorean theorem for this, we can extend the Pythagorean theorem to 3 dimensions and even more. Distance squared equals the x component squared plus the y component squared plus the z component squared. So the Pythagorean theorem, or we might say the Pythagorean distance formula, extends to more than 2 dimensions as well. Even if you've got like a 5-dimensional vector, you could still say the length squared equals a squared plus b squared plus c squared plus d squared plus e squared. You can't really draw out a 5-dimensional vector, but the mathematics still applies. So this a squared plus b squared plus c squared is the length of the vector squared, which we would call magnitude of u squared. So you can calculate the magnitude from the components using the usual Pythagorean distance formula, but you can also write magnitude squared as the vector dot itself. And this is often a very useful way of writing magnitudes because it means we can use everything we already know about dot products to manage that. Any other questions on that so far? And by the way, another very useful way of, or at least often useful way of writing out dot products. Have you seen the idea of matrix multiplication yet? Like a matrix times another matrix?
Not in this class, no.
Okay, that's going to come up pretty soon. I really think they ought to introduce that first. I'm not sure why they don't.
For some reason, they're starting on chapter 3 with the vectors because they say it's most closely related to 21C. Like that's the idea behind it. But having taken this class in the past, it feels kind of like a weird way to jump in the middle and then like we're going backwards.
Very strange sort of order. But the main idea is that a dot product of vectors can also be written as a matrix multiplication. Like if we write these in the usual notation of height by width, so vector u is a 3x1 matrix. Vector v is also a 3x1 matrix. And if you're looking at matrix multiplication, you can't multiply a 3x1 matrix times a 3x1 matrix because the dimensions don't match up. But what could you do to this first vector in terms of being a matrix that would make the dimensions match up properly?
Isn't there a way to turn it into a row instead of a column?
Yeah, if we transpose it.
Yeah.
So if we take U transpose, the transpose of a matrix, including a column vector, just means you rewrite every row as a column and vice versa. So U transpose would be A, B, C as a row instead of a column. So that's what this notation means. It's not to the power of t. It just means transpose, turn the columns into rows and vice versa. So every column of the original matrix becomes a row of its transpose. Every row, like this row of just A, becomes a column of just A. So we're just swapping rows versus columns. And that's now a 1x3 matrix. And V is 3x1. Since the inner dimensions match up, 3 and 3, we can actually multiply these as matrices. So U transpose A, B, C, multiplied by V as it is, X, Y, Z. Typically, the way we multiply matrices is combining a row of the first matrix and a column of the second matrix. So row and column, A times X plus B times Y plus C times Z is exactly the same thing we get from the usual idea of dot product. Yes, in general, if you're multiplying matrices, like let's say you've got matrix A times matrix B. If matrix A is, let's say, 5x3, and matrix B is, let's say, 3x2, the inner dimensions matching up is what tells you, yes, this can be done. Because multiplying matrices means you're combining a row of the first matrix and a column of the second matrix. So a row of the first matrix and a column of the second matrix have to be the same number of numbers. So 3 across and 3 down have to match. And then the outer dimensions, the 5 and the 2, tell you the dimensions of the result. So AB is going to be a 5x2 matrix. So in general, anytime you've got matrices being multiplied, and we typically list the dimensions as height by width. So 5x3 means 5 high and 3 across. the inner dimensions have to match up for this to be even possible. Like if this was a 5 by 3 times a 5 by 2, it would not be possible to multiply those in this order. But the inner dimensions matching up means it's possible to multiply them. And the outer dimensions tell you the dimensions of the result. So AB would be a 5 high, 2 wide matrix, 5 by 2. In the case of vectors, U transpose times V would be a 1 by 3 matrix times a 3 by 1 matrix. The inner dimensions, the 3's matching up means this can be done. And the result is going to be 1 by 1. In other words, just a single number. And that single number is the same as U dot V. So any dot product of vectors can be rewritten as matrix multiplication. It's just the transpose of the first vector times the second vector exactly as is. And sometimes this makes it look more confusing, but the main advantage of it is that by writing it dot product as matrix multiplication, we can now use everything we know about matrix multiplication, or everything we're eventually going to find out about matrix multiplication, to analyze dot products. And that's often very useful because you can then combine that with other matrix multiplication stuff. For instance, you can write the magnitude. Magnitude of a vector is going to be square root of the vector dot itself. So you can then write that as square root of U transpose times itself. So magnitude can also be written in terms of matrix multiplication. Again, just so we can combine that with anything else we know about matrix multiplication. Any other questions on that so far? Yeah, go ahead.
I don't know. I guess I'm still a little confused. So it's like this is matrix multiplication, and earlier we were doing dot product, but like they both basically just got the same answers, AX plus BY plus CZ.
Yeah, it's essentially just two different ways of writing the exact same thing.
Okay.
A dot product means you're multiplying the corresponding values and adding them up. So
Okay.
AX plus BY plus CZ. Whereas the matrix multiplication of U transpose times V means we write U as a row instead of a column and multiply by V as a column. But the way matrix multiplication is defined, you're combining a row and a column, so AX plus BY plus CZ, and you get the same result anyway. So U transpose times V is just a way of rewriting U dot V as a matrix multiplication problem.
Okay, got it. And then on the bottom where you said like the AB 5 by 2 on like the right, I was a little confused about that part.
The idea is if you're taking a 5 by 3 matrix and multiplying it by a 3 by 2 matrix, like let's say you have A is 5 high and 3 across. So let's say each one of these dots represents some number. I'm not going to write out all 15 numbers, but let's say this is matrix A, which is 5 by 3. And then matrix B is 3 by 2. The reason these can be multiplied in the first place, again, we're combining a row of the first matrix and a column of the second matrix. So you take, for instance, this row and this column, and you'd be multiplying this times this, plus this times this, plus this times this. So this times this, plus this times this, plus this times this. And that's going to get you a number. And where that's going to go in the result since that's combining the first row and the first column, the result is going to be in the first row and first column. But you could also combine, for example, the second row and the first column. So this times this, plus this times this, plus this times this. Combining second row and first column, that'll give you a number, which is going to go in the second row, first column of the result. And you could also combine third row, first column, fourth row, first column, fifth row, first column. So that's going to give you 5 values in this first column. But then you could also combine, for instance, the first row and the second column. That'll give you a number that you'll put in the first row, second column of the result. And then second row, second column would go in the second row, second column of the result, and so on. So there's going to be 5 rows that you're combining with 2 columns, which means the result is going to have 5 rows and 2 columns, because there's 5 times 2, 10 different ways of doing that.
Thank you. That makes all my sense now.
And we're going to get into more detail in that later as well, just the idea of matrix multiplication, how to do it, what we can use it for. But that's the core idea. You're combining rows of the first matrix and columns of the second matrix. Dot product and inner product. Inner product is a more general term. There's many operations that can be called inner products. Dot product is one example of an inner product. And the reason dot product is called an inner product, where this term comes from in the first place, is that the T is on the inside of the U and the V. It's also possible to write an outer product. So this dot product is also called an inner product because the T is on the inside. There are other operations that also fall into the category of inner product. So dot product is one example of an inner product, but inner product is a broader category. In general, an inner product is any operation that takes 2 vectors as input and gives you a scalar as output. But the dot product is just one example of that. And it also has to follow certain rules, but it takes 2 vectors as input, gives you a scalar as output, and follows certain rules. Dot product is one example. In contrast, there's also what's called the outer product, which would be U times V transpose. So U is still a 3x1 column. V transpose is a 1x3 row. Can those be multiplied? Yeah. The inner dimensions, 1 and 1, match up. But what do you notice about what the result is going to look like? Is the result still just going to be a 1x1 scalar? No, what would the result be? Or what sort of thing would the result look like? Yeah, these outer dimensions, the 3 and the 3, that tells us the result. The result is going to be not just a scalar, but a 3x3 matrix. And the reason we get that 3x3 matrix, if we actually write this out, like U as a column, A, B, C, times V transpose as a row, X, Y, Z, by multiplying row times column in this order, sorry, column times row, we're still going to be combining a row of the first matrix times a column of the second matrix. There's no addition involved here. It'll just be A times X. So top row, left column is going to be AX. And then if we take a look at, for instance, the top row, second column, A times Y. So the top row, second column is going to be AY. Yes, an inner product is always going to have a scalar as the result. By definition, an inner product always is an operation that takes 2 vectors as input and gives you a single scalar as the output, and also has to follow certain rules. Like, for instance, the inner product of a vector n itself will always be a non-negative result. But you could keep going. For instance, let's say the second column or second row and third column, B times Z, so that's going to go here. And you could keep filling those in, A times Z, B times X, B times Y, C times X, C times Y, C times Z. So we get a 3x3 matrix whose values are just the different ways of combining something from the first vector times something from the second vector. So the outer product, U times V transpose, gives you an entire square matrix as a result. And that's called the outer product because the T is on the outside instead of the inside. So inner product is any operation that takes 2 vectors as input and gives you a scalar as output and follows certain rules. the dot product is one of those inner products. So usually when we say inner product, we just mean the dot product. It's just that there are also other operations that also count as inner products. Then outer product takes two vectors as input and gives you an entire square matrix as an output. And that's used in some formulas as well. But dot product is usually much more useful. Any other questions on that so far?
Oh, a quick question.
Yeah, go ahead.
So I don't know if this is like, I'll just ask it. So it's always going to be like u times v. It's never going to be like v times u, right?
Well, it's whatever order it's listed in. So if the problem says v times u, then that's what you calculate.
Okay, and in that case, if it's v times u and the t is on the u, is that going to be outer product?
Yeah. For instance, if we wrote v times u transpose, that would be the outer product of v and u.
Okay, got it.
But if we wrote v transpose times u, that would be an inner product. It's the same as the dot product of v dot u.
Okay. Got it.
And inner product or dot product is commutative. That's another important property of the definition of inner product. That inner product of u and v has to be the same as inner product of v and u. I don't think that has to be true for outer product though. And in general, matrix multiplication is not commutative. That matrix A times matrix B is not the same as matrix B times matrix A. In fact, if one of them doesn't even have to be possible. For instance, if we go back to AB where A is 5 by 3 and B is 3 by 2, if we swap the order, B is 3 by 2 and A is 5 by 3, this order isn't even possible because the inner dimensions 2 and 5 don't match up. So if we multiply A times B, B times A will not only be not necessarily the same, it won't necessarily even be possible. But even if it is possible, it might give you a different result. So you can't assume that A times B and B times A give you the same result. Matrix multiplication in general is not commutative. X plus y dot z. Yeah, one of the other important properties of dot products, and in fact, inner products in general, is that they are distributive. So for instance, if you've got vectors A, B, and let me say U, V, and W. If you've got two vectors added together, and then dot product with another vector, dot product is commutative. Or sorry, not commutative. Actually, it is commutative. But the important thing is, in this case, dot product distributes over addition. So you can take the dot W applied to both the U and the V. So you get U dot W plus V dot W. And you can try this out with specific numbers. Of course, a single example doesn't prove that it's true, but working it out with an example can be a useful way of checking, yeah, this at least seems to make sense. Like if you actually fill in some numbers for U, let's say 1, 2, 3, and V, let's say, is 4, 0, negative 2. And let's say W is another 3 by 1 vector, let's say 1, 5, 1. You can try working this out both ways. You could add the vectors together first, 1 plus 4, 2 plus 0, 3 plus negative 2, and then take the dot product of that with 1, 5, 1. So if we try it in that order, yeah, adding them together first and then taking the dot product with W, we should get a number, not a vector, 5 times 1 plus 2 times 5 plus 1 times 1. In other words, 16. So that would be if we add them together first and then apply the dot product. Or if we take the dot products individually, U dot W, so that'd be 123.151. So 1 times 1 plus 2 times 5 plus 3 times 1.
14.
In other words, 14. And then V dot W. If we take that dot product separately, 4 times 1 plus 0 times 5 plus -2 times 1. So 4 plus 0 plus -2 would just be 2. 14, that's u dot w, plus 2, that's v dot w, is indeed the same as 16. Again, using specific numbers means we're not proving it. We're just looking at one specific example, but we can at least see that it's true for this example. That if you add them first and then take the dot product, or if you take the individual dot products first and then add the results, you still get the same final answer. So it doesn't matter if you add the vectors first and then apply the dot product, or take the dot products individually first and then add the result. In other words, dot product distributes over addition. And the order doesn't matter because dot product is also commutative. This will also equal w dot u plus v, or v plus u. Dot product is commutative, so order doesn't matter. Any other questions on that so far?
I'm having a little bit of trouble understanding the difference between the inner product and the outer product. Like when would you, like, is there a difference in the way you do them? I'm a little confused.
Yeah, inner product is essentially the same as dot product for purposes of Rn vectors. Inner product takes two vectors as input and gives you a single scalar, just one number as output. Outer product takes two vectors as input and gives you an entire square matrix as output.
Oh, all right.
So like instead of adding ax plus by plus cz, you'd be looking at all possible combinations of multiplying.
Yeah, making the whole matrix.
Yeah. Excuse me. What else? Oh, also one other important property of dot product we should look into, the coastline formula. Essentially just a bunch of different stuff you can do using the components, because we know that, for instance, you can calculate magnitude of a vector by taking the dot product of the vector and itself, and then taking the square root. You can calculate the dot product as long as you have the components. So as long as you have the components, you can also calculate the magnitude, which essentially tells you how long or how large the vector is, ignoring the direction. Also, if you're taking the dot product of two vectors, u dot v, you calculate that by definition by multiplying the components ax plus by plus cz, adding them together. But it also so happens that that equals the magnitude of the first vector times the magnitude of the second vector. This is actually going to be the largest possible. If u and v happen to be in the same direction, then u dot v just gives you magnitude times magnitude. But if they're in different directions, you also have another multiplier that depends on the angle between them. And it turns out that multiplier is cosine of the angle between them. So if you've got vector u and vector v, and there's some angle theta between them. If you take the dot product of u dot v, the result that you get from the components is going to happen to equal magnitude of one vector times magnitude of the other vector times cosine of the angle between them. And you can prove this using geometry. We're not going to go into the details of the proof here, but some of the important results of this, first of all, you can calculate the dot product based on the components. You can calculate magnitude of u and magnitude of v separately based on their components. If you can calculate all those, what's the only unknown left in the equation?
Theta.
Yeah, theta, which means you can then solve for theta by dividing both sides by the magnitudes. And then taking the inverse cosine. So it's actually possible to use this to calculate the angle between the vectors. If all you have is the components of each vector, you can take the dot product of the vectors by using the components, calculate the magnitudes using the components, divide u dot v divided by the magnitudes multiplied together. That gives you a ratio which should be between -1 and +1. Take the inverse cosine of that ratio, and that inverse cosine will tell you the angle between the two vectors. So this is one of the very useful results or very useful applications of this idea of dot product. You can use it to find the angle between two vectors if all you have is the components. And I want to emphasize this applies even if you're in more than 3 dimensions. Even if you've got like 5x1 vectors, let's say 1, 2, 3, 4, 5, and 7, 0, 7, 0, 7. There's no way you can draw these vectors in a 3-dimensional universe. We live in a 3-dimensional universe. These are 5-dimensional vectors, so we can't really draw them out and measure the angle with a protractor. But you can use this formula, inverse cosine of u dot v divided by magnitude u times magnitude v, to calculate what the angle between them is, even if you can't visualize what they look like. So these formulas that we create using 2 or 3 dimensions can be extended to 4, 5, 6, as many dimensions as you want. In fact, these don't even have to be n×1 vectors of numbers. You can also define certain other things as vectors. For instance, polynomials can be treated as vectors. Functions can be treated as vectors. And as long as you can define something like a dot product, as long as you can define the inner product of 2 of those things, excuse me. For instance, there's a way to define inner product of 2 polynomials or inner product of 2 functions. You can use this same structure to calculate the angle between 2 functions, even though it doesn't really make sense to talk about geometrically the angle between 2 functions. You can still define something that we can call the angle between those 2 functions, which basically describes how different those 2 types of functions are from each other. And some useful results of that. What's the largest cosine can possibly be?
1.
Yeah. So that means the largest the dot product can be is magnitude times 1. And that happens when theta is what angle?
0. Or 180?
No, yes, it should be 0. If it's 180, then it would get -1. So if the 2 vectors are in the same direction, if you got vector u and vector v in the same direction, the angle between them is 0, so you get a large positive value for a dot product.
Oh.
If they're in exact opposite directions, what's the angle between them?
180.
And cosine of 180 degrees would be?
-1.
Right. So if the vectors are in exact opposite directions, you get a very negative dot product. In fact, the dot product will just be negative magnitude times magnitude. What if they're perpendicular, though? If they're perpendicular, what's the cosine of a right angle?
0.
Right. So that means if u and v are perpendicular, then u dot v will be 0. So this is another very convenient use for dot products. If you take the dot product of 2 vectors and the result is exactly 0, you know the vectors are perpendicular. In fact, this is how we define perpendicular or orthogonal in terms of vectors. If the dot product is positive, they might not be exactly parallel, but they're at least mostly in the same direction. Their angle between them is acute. Whereas if the dot product is negative, that means they're mostly in opposite directions. There's an obtuse angle between them. So this is one of the very useful results of the dot product. Even just knowing whether the dot product is positive, negative, or 0 tells you some very important information about how those vectors are related. 0 means the vectors are orthogonal to each other. Positive means they're in mostly the same direction. Negative means they're in mostly opposite directions. Any other questions on that? And just real quick on that example that you brought up on Discord, let me pull that up. I was essentially asking, here's a bunch of calculations you can do with vectors. Are the results going to be scalars or vectors? For example,
hello? Can you hear me?
Yeah, go ahead.
Oh, where do you put these recordings?
They're going to be on a YouTube playlist linked from math.ncheese.org. And I'll post those on the Discord as well. But you can find all the playlists on math.andcheese. I'll post this in the chat. math.andcheese.org/M22A is where I'll link the playlist.
So it'll be in the winter one, or?
Yeah, I'll make a new playlist for this quarter.
Oh, okay, thank you.
But just as a quick example, let's say we're talking about, let's say one of these is vector u divided by magnitude of u. And it's asking, is the result a real number or a scalar? Sorry, a scalar or a vector. U itself is a vector. Is magnitude of u a vector or a scalar? Yeah, this is a scalar. So that's going to equal something. However, if you take a vector and divide by a scalar, is the result going to be a vector or a scalar? Yeah, the result is a vector. Exactly. Because if you take a vector and multiply or divide by a scalar, you're not really changing the direction. You might be changing to the exact opposite direction if the multiplier is a negative value. But you're always going to end up with a new vector that's at least parallel to the original vector. It's just modifying the size. So vector u divided by its own magnitude, the result is going to be a new vector. It's just going to be a different length. In particular, if you divide it by its own magnitude, what's the new magnitude going to be?
This is important. I remember going over this.
Yes, it will become very important later on. For example, let's say vector u has length 5. If you divide it by 5, what's the new length?
1.
Right. So if you take any vector and divide by its own length, you get a unit, yeah, exactly, a unit vector. A new vector in the same direction, but with length exactly 1 unit. So this is a very useful way of standardizing, or we usually call it normalizing the vector. Dividing out the magnitude gives you a new vector that is magnitude 1. It's a standardized unit magnitude, but it keeps the direction. So a vector divided by its own magnitude keeps the information about the direction, but gets rid of the information about the size. So this is essentially a way of writing out just a direction without caring about size. All right, I've got to go get ready for my next workshop, but feel free to let me know if you have any other questions or any examples you want to request for next time, and I will see you then.